Good morning, everyone. So today we are going to learn about the designing problems of context-free grammar. Okay, as I told you, the Chomsky hierarchy, there are four types of grammars: type 0, type 1, type 2, and type 3. Okay, so type context-free grammar is the type 2 grammar, and the language for the context-free grammar is the context-free language. The language for the context-free grammar is the context-free language, and the machine that can understand this language is the push-down machine. Okay, so we are learning about the designing problems of context-free grammar. So this will be the last lecture for the designing problems of context-free grammar. So let us see some of the practice problems of context-free grammar. Okay, so it is a type 2 grammar. Just have a revision about this grammar. Every grammar has a particular language. So the computer languages can be termed as the formal languages. The language has the grammar, and the language has the set of symbols. And by following the set of symbols, we create the word, and the word or the sentence is formed by following the grammar. Okay, so this is the CFG. Now, the grammar can be defined as grammar G is equal to VTPS, where V is the set of variables which are capital letters, T is the set of terminal symbols which are the small case letters, and P is the set of rules that are called as production rules, and S is the starting symbol. Okay, so a grammar is a context-free grammar. It is also called as a type 2 grammar. The language is the context-free language, and the machine is the push-down machine. And the grammar is defined as VTPS, where it is a group of four elements: set of variables, set of terminal symbols, set of production rules, and the starting symbol. And the rules are of the type of A generates alpha. Okay, so where your left hand side is the single variable and the right hand side is the group of variables and terminals. So you need to remember always whenever I say context free grammar, you need to remember this, that it is a group of four elements. VTPS, V are the capital letters, T is the small case letters, and the rules are of this type: A generates alpha. Okay, so we have seen this example: a raised to n, b, a raised to n, where number of a's are similar, and we can have a parse tree like this. Like here, we start from the starting symbol s, left hand side 1a, at the same time right hand side a should be generated, and repeat the process. And you can stop the recursion by the variable b, and then define the grammar like this, that a is equal to aca, and to stop the recursion we can say that it is equal to c is equal to b. Okay, so always whenever there is a problem, and if you are confused, if you are having confusion about designing of the problem, you have to draw the parse tree first. Draw the parse tree for this particular language, identify the words of the languages. Okay, so I'm just telling you some of the steps how to design the grammar, but it is not a hard and fast. Again, it is a trial and error method, and you need to because it is your design, and you need to verify your answer, that whether it is correct or not. So what is here? The set of words are: prepare the set of words, see the language, read the statement carefully, try to understand, interpret it properly, and then find out multiple words belonging to the language. By looking at the words, you create the parse tree, and then by looking at the parse tree, you can start writing the rules. And when we start writing the rules, we have to start writing the rules from capital S. So first you write the rules for the capital S, and then resolve all the variables. Variables are always the nodes of this tree, and terminals are the leaf nodes. So this way you can go ahead for designing problems. Okay, so let's see some of the new problems. Context free grammar. Just now I told you that it is a CFG, language is CFL, machine is push down machine. Rules are A generates alpha type of rules, where alpha indicates group of or the combination of variables and terminals, and even S can appear to the right hand side. That is the speciality of context free grammar. Your starting symbol can appear to the right hand side, wherein context sensitive language, your starting symbol cannot appear to the right hand side of your LHS. And for 0 raised to n, 1 raised to n, remember always that this is the rules. Like s is equal to 0 s1. So for 1 0 1 1 is generated, and to stop the recursion, we can say s is equal to epsilon, where the n is greater than or equal to 0 in that case. Otherwise, it will be 0 1 for 1. Okay, so you need to remember that condition, whether it is greater than or equal to 0 or greater than or equal to 1. That is also important concept when you do the designing. Okay, and I told you that this always remember the 0 raised to n, 1 raised to n is not a regular language. It is a context-free language. Why? Because it follows the pumping lemma. Like if we assume that it is a regular language, it should follow the pumping lemma, and but we come to know that it is not following the pumping lemma. So it is not a regular language. So we take a word that 000, 111 and divide the word into three parts, where b is equal to 00, is repeated for any number of times. So if it is repeated for three times, then we get the resulting string, and the resulting string does not belong to 0 raised to n, 1 raised to n, because number of zeros and number of ones are not same. So that means this particular word created from this language does not follow pumping lemma, so it is not a regular language. So pumping lemma is used to prove that a given language is not regular. It is not used to prove that the given language is regular, but it is used to prove that the given language is not regular. Okay, so this way we go ahead with the context free grammar, and this is the parse tree for 0 and 1. So see this parse tree and just keep it in the mind that 0 s1 and then 0 s1 any number of times, and then to enter recursion it is epsilon. It is a revision, but I am just taking the revision because this designing problems, for designing problems, all these concepts which I am telling you and repeating are must to remember. And always remember these two examples, a raised to n and a raised to n, b raised to n, and convert anything given to you in any one of this format. Okay, so then you can design the problem properly. So for a raised to n, I'm saying that a is repeated for n number of times. So if a is repeated for n number of times, my rules are s is equal to as. So it is a recursion. So a is for s any number of times. So a again, again a, and it is n is greater than or equal to 1. So my terminal or ending of the recursion is with s is equal to small n. Okay, this is the parse tree for that. That s is equal to as, s is equal to as, s is equal to as, and to stop the recursion, it is equal to a. So this way, you need to remember a raised to n ka example and a raised to n, b raised to n ka example always when you are doing the designing. Okay, so that's why I'm repeating this. So a for any number of times means s is equal to as, and remember it should be the right recursion. You should not write the rule as sa. Whenever you are using any recursion, try to make the recursion at the rightmost location in the rule, or in the middle. Like in a raised to n, b raised to n, number of a's and number of b's are same. So we are saying that s may generate one a and one b. Again, the second S may generate one A and one B. Again, the third S will generate one A and one B. Like this, it will go on. And as it is n is greater than or equal to 0, my recursion is ending with S is equal to epsilon. And here the recursion is ending with S is equal to A. Okay, so this way it is going to happen. And then the parse tree is S is equal to A S B. Again, S is equal to A S B. And then S is equal to epsilon. Okay, so this way, remember all this, both the parse trees in your mind, keep it in mind, and then only you can solve the problems. Okay, so today's lecture is just a light lecture with 5 6 designing problems, and with that I feel that we have done sufficient practice of designing problems. So next lecture we will start with the next topic of the context free grammar. Okay, so today some designing problems. And now I told you that suppose in your C language, if you have a statement like this, that A plus B is in the bracket multiplied by C, and that is assigned to suppose D. So this is your expression. Now this particular context free grammar ka application is in the compiler ka second stage. That is the syntax analysis stage of the compiler. In syntax analysis stage of the compiler checks that whether the syntax of the statement is correct or not. And if it is not a correct syntax, it gives you the syntax error. At the same time, the syntax analyzer creates a parse tree like this. Like for this particular, our language is a very simple language, A raised to n, B raised to n. But your C language is a very big language, so there are many parse trees. But for the particular statement, the syntax analyzer will create the parse tree like this, where it is saying that this multiplication is the operator, that is the variable, plus is the operator, that is the variable, and small a, small b, small c are the terminal symbols. Okay, even we can include these brackets in the parse tree. Okay, but we are ignoring the bracket in this particular diagram. So what, because of the brackets, the parse tree generated is like this, and the syntax analyzer of the compiler will check for the syntax. The syntax is correct. There is no double bracket is not there or double plus is not there. Like this, it will check for the syntax. Now it is going to generate the parse tree. Because of the left hand side bracket and right hand side bracket, it will come to know that first it has to add A with B, and then the answer is calculated here, and that is multiplied with C, and then you may have equal to sign here, so that this right hand side will be assigned to the left hand side. You can have even equal to as a root node here, and to the left hand side you may have the variable D, and then the value of this entire expression will be assigned to D. Okay, this way you can again go on expanding this parse tree. So just try to visualize this context-free grammar is extensively used in the syntax analyzer of the compiler. And by looking at the statement, if the syntax is correct, compiler is going to generate the parse tree, and the parse tree is referred by the runtime environment when the program is actually in execution. So when the program actually starts executing this particular statement, when the system or operating system starts executing this particular statement, machine language instruction, that time it will add A plus B, and that result will be multiplied with C, and that will be assigned to D. Like this, it will understand that first addition and multiplication. And if you don't write the curly bracket, then the parse tree will change. And here you will have the B into C is multiplied first, and then that will be added to A, and that will be assigned to D. Like this it will happen. So the parse tree will change. So parse tree tells the execution system how to execute the program. And so it is very important that the generated parse tree should not be ambiguous. Like with the leftmost derivation of your expression or rightmost derivation of your expression, if you are getting multiple parse tree for the single expression, then your language or the grammar is ambiguous. So whenever you are designing your grammar, the grammar should be designed in such a way that it should not be ambiguous. It should be unambiguous grammar. Anyway, whatever the method you follow, rightmost derivation or leftmost derivation, the same parse tree should be generated. I have shown you one example of leftmost derivation and rightmost derivation, where you always resolve the leftmost variable in your expression, and in rightmost you always resolve in the parse tree the rightmost variable, and you generate the parse tree finally. Okay, so that is called as LMD and RMD. If LMD and RMD both are same, that means and the parse tree is exactly same, then you can say that the grammar is unambiguous. Okay, so let's have a quick recap before starting of the problem. Context-free grammar is the type 2 grammar of the Chomsky hierarchy. Context-free grammar का language है context-free language. Context-free language is understood by the machine, push-down machine. And context-free language में or context-free grammar में all the rules are of this type, where your left-hand side is a single variable, right-hand side is the group of variable and terminal symbols. B union T bracket star, and when you the application of context-free grammar is in the compiler construction, where in the compiler you have a particular phase called as syntax analyzer. That syntax analyzer checks for the syntax of the statement, and it generates the parse tree, and the parse tree is referred by the execution environment whenever the statement is executed by the system. Okay, the pass tree, according to the pass tree, the statement or expression is executed. So as per this pass tree, unless and until you resolve a plus b, you cannot multiply it with c. So first, it compulsorily it has to do the addition, and then only multiplication will happen. So pass tree decides that. And even whenever you are designing your own language, you need to write down the grammar for the language. So that time also this context free grammar kind of designing concepts are extensively used in creating your own language. Okay, so now see the problem. I think this problem we have done last time, that a raised to I, b raised to j, c raised to q. And what is the statement that is given to you is that I plus j is equal to q. So if I plus j is equal to q, as I told you that like previous example, convert everything in the form of a raised to n or a raised to n, b raised to n. Okay, so any expression given to you, you convert it into either a raised to n, or split it into either a raised to n or a raised to n, b raised to n kind of statement. So here for this particular problem, we see that I plus j is equal to q. So now we have to convert it in any one of the format. So what we can do is that if I plus j is equal to q, that means c can be divided into two parts, because c is for q times. C is for q times, so c is divided into two parts, and it can be c for j times and c for I times. Okay, so because I plus j is equal to q, c raised to q, matlab c is for q times, can be rewritten as c for j times and c for I times. So we can rewrite this particular string in this way: a raised to I, b raised to j, c raised to j, and then c raised to I. And I'm not writing I before j because I want to convert my expression into b raised to n, a raised to n, b raised to n. So here, if I write j first, this b, number of b's and number of c's are same. Number of b's and number of c's are same. So it is, so we can have a group of this. And even this number of a's and number of c's are same. So we can have a group of a and c. So just observe this: number of a's and number of c's are same. And here, so we can have a rule for this, that if a is generated, the corresponding c should be generated. Again, A is generated, the C will be generated. And then we resolve this, that when B is generated, C should be generated. So finally, you will get total number of C's is equal to total number of A's and B's. This way, we will solve the problem. Okay. So what I'll say is that S is equal to A, S, C. Okay. If it is A, S, C, then A for any number of times and C for any number of times. Will be done, and the recursion is happening. And whenever you want to stop the recursion for a and c, apply the rule a x c, or only x. Okay, only x is the more relevant option. Okay, a x c से अच्छा है, so we will have it as a only x, because a and c are already generated here. But that is also correct. That is also correct. So, but I'm saying that it is equal to x. Either AAC generated for many number of times, and then x is generated to stop the recursion. Say x is generated. Now x is going to generate b and c. So x is going to generate b and c. So left hand side b will have the corresponding right hand side b. And to stop the recursion, it will be bc, because we are saying that it should be there at least for once. At least for once. Okay, that's why I've written down here AXC. Okay, if it is at least for one say, so then we have to write here AXC. So this is a trial and error method. You, in one shot, you cannot say that the answer is correct. You will have to again revisit. When you design it, you have to revisit and check it. Now I realize that A and C both are needed, because it is actually once. So the user can apply the first this rule directly. When he is applying this rule directly, A and C is there for at least once. So like this is the grammar. Then take the second example. Okay, so we will see this example now. What they're saying here, generate the context-free grammar for the language. And the language has zeros for I times, ones for j times, and zeros again for k times. And the relation between I, j, k is j is greater than I plus k. So number of ones should be greater than the number of zeros of both the sides. So what they're saying, j is greater than I plus k. So what I can say is that means j number of ones are there for I number of times, number of ones are there for k number of times, and still there are some extra ones. At least one will be there. Okay, so that's what I'm taking here the example. I is equal to 2. If I is equal to 2, then there are two zeros. So here two zeros are there. And I suppose k is equal to 3, then here three zeros are there. And now I plus j is equal to 5. So number of k should be at least equal to 6. So I am having a string as 0, 0, 6, 1 and 3 zeros. I am assuming I is equal to 2, k is equal to 3. So if I is equal to 2, then here there are two zeros and here there are three zeros. And then number of ones are greater than that. So number of ones are greater than 2 plus 3, that is equal to 5. So that is, it is greater than 5. That is minimum, it is 6. So now again I can split this number of ones. So what I'll do is that I'll here I is equal to 2. So I'll say that two ones are here. Okay, so these ones are there for I number of times. So I'm having the string, I am rewriting this string as 0 raised to I, 1 raised to I. And then for this right hand side portion, my zeros are for k times. So I'll have ones for k times. Okay, so 1 raised to k and 0 raised to k. And now here in between, I can see that there are p times of ones are there, where p is equal to j minus I minus k. P is equal to the number of ones are always greater than I plus k. So the remaining number of ones is equal to p. Okay, so what I think you have understood that. And if you any issue, then just unmute and ask me. Okay, so you have I number of zeros and k number of zeros, and then I number of ones, k number of ones, and the remaining ones are there here, and they are p times. Okay, in the diagram it is 6 ones, so only one is here. Okay, so now if I observe this, I can make a group of this 0 and ones. It is same. So I've converted it to a raised to n, b raised to n. Here also I have converted it to 1 raised to n, 0 raised to n. So now writing rule for this is very easy. And then here it is 1 raised to n. This 1 raised to p hai, that is equivalent to 1 raised to n ka rules. So that's why always remember that first two problems. And then you can solve any problem. So now I can divide my string into three parts. So I'll say that my S will be A, B, and C, where A is equal to this, B is going to generate this middle portion, and the C is going to generate the third portion. So I'll say that my S is equal to X, Y, Z. So while writing the rule, I can now decide that my S is equal to X, Y, Z. All three are compulsory. And what is X? X is going to generate number of zeros and number of ones. So I'll say that X is equal to 0x1 or epsilon. Okay, nothing is mentioned whether greater than 0 or greater than 1. So we can assume that it is anything, means it can be 0 also. So if it is 0, then it is epsilon. So for 0, the 1 is generated. To stop the recursion, x will be equal to epsilon. Then for y, 1 raised to p. So y is equal to 1y or 1. And then z will be equal to 1z0. Z will be 1, Z0, and to stop the recursion, it will be epsilon. Okay, to stop the recursion, it will be epsilon. But why cannot be epsilon? Because always they are saying that j is greater than I plus k. So if I is equal to 0, k is equal to 0, it will be 0 plus 0, and j will be greater than 0. Means at least for one is there. So minimum length string for this particular language is 1. Okay, so that's why here there will not be any epsilon. And then these are the rules for the language. Okay, so I'll write them and then you verify your answer. Okay, so write down the final answer as the language is VTPS, grammar is VTPS. V is equal to all four variables x, y, z, and terminal symbols are a comma b. Okay, so this problem we did yesterday. This was 0. After that, either 0 or 1, then 0 1, either 0 or 1 for any number of times, and then 1. So for this particular part, we can have a variable. So I'll say that I have a variable x for that. So I'll say that my s is equal to the 0, x, then 0 1, x, and 1. And then you write down the values for x. X is equal to either 0, 0x or 1x or epsilon because it is star closure. Okay, and then the final answer. So I think this is correct. This also you have solved yesterday. This is your either 0 or 1 and there is no star. So this can be one variable. Then this can be 1 star will be one variable and 1 plus 0 1 star this can be a variable. So I'll have s is equal to three variables, that is a b c. S is equal to a, b, and c. Now my a can be either 0 or 1. So it is simple, either 0 or 1. B is 1 star. So B is equal to 1B or epsilon. And then C will be either 1, either 1 or 0 1 string. So for 0 1 string, I'm taking another variable capital D. And then capital D will be 0 1 D or epsilon. Okay. So this way you go on splitting the problem to either 0 raised to n or 0 or 1 plus and then solve. Now see here the set of strings of odd length with the middle symbol equal to 1. Okay. Set of strings with odd length. So if it is odd length and the middle symbol should be 1. So to the left hand side of 1, there can be anything either 0 or 1 or to the right hand side there can be anything either 0 or 1. But for one left symbol, one right symbol should be generated so that it will remain as a string of odd length. Okay, so anyone can suggest me what to write here? The rules. Write down your answer in the chat box. The question is this, that set of strings of odd length. Set of strings of odd length. And the middle symbol is 1. So I can identify my word may have either 0 or 1 here, but one symbol here corresponding one symbol here. To the left hand side there can be 0, to the right hand side there can be 0 or 1. To the left hand side there can be 1, right hand side can be 0 or 1. So anyone can suggest me what to write? Write your answers in chat box. It is x1x. Tanisha is saying. Nisha is saying x1x. Okay. Am I audible properly? Okay. So if I'm saying x1x, then let's write. Okay. My answer is this. Here you can do that way also, but then you need to define x, and x will be either 0 or 1. If you say x1x, then what will you do after that? It is a trial and error method. This answer can also be the correct answer. X will be equal to 0x or 1x. But if you do that after that, then you may go on applying to the left hand side the recursion for 4 times, and right hand side only once. And then your number of ones to the left and number of ones to the right will not remain same. So initially you can think like this, but it is not a correct answer. You have to try. You will find out that this is not generating the proper strings. So you have to stop and go back and again try with the next option for the problem. Okay. See here, if you are saying x1x, for this x, what you will do, you may write a recursion, and the recursion, suppose it is applied for 3 times repetitively, the length of the string to the left hand side will be 3. And here to the right hand side, if you are applying it for only once, the length of the right hand side will become 1. And there is no guarantee that the resulting string ka length is odd. The question is that your string should be of odd length. String should be of odd length. So it can be either 3 or 5 or 7. So means one variable to the left should have the corresponding right variable uh, to the right side. So I can use this optimized solution that s is equal to either 1 if n is equal to 0. So the odd length, matlab, the length of the string is 1. Or it can be 0 as 0 or 0 as 1 or 1 as 0 or 1 as 1. And you can go on applying the recursion any manner, any rule, any time. Okay, so this is the simple answer for this question. Now the next question you also solve and write into the chat box. Even length strings A B C D star with the middle two symbols equal. Middle two symbols are equal. That means middle two symbols can be either AA or BB or CC or DD. Okay, and the length of the string should be even. So how the length of the string will become even if you add one symbol to left and one symbol to right, the resulting string will become even length. So what can be the answer? So answer will have many rules. Middle two symbols are AA, BB, CC or DD. Write down your answers in the chat box. At least for A you can write down. Okay, so I'll just say that it can be S is equal to ASA or ASB or ASC or ASD. Because my S will be finally, I'll stop the recursion with any one of this. Or S can be BSA or BSB or BSC or BSD. Or it can be CSA, CSB, CSC and CSD. Or it can be DSA, DSB, DSC or DSD or this to stop the recursion, or it can be AA, BB, CC or DD. So it will be the resulting string will always be the even length string. This will be the answer, a big answer for this particular question. Okay, so now move to the next problem. Matching parenthesis. Design the context-free grammar for matching parenthesis. Matching parenthesis. So I have taken this example that I have tried to use both the combinations. That first bracket opening and closing, and then the second opening and closing. This is also the matching parenthesis, which is used in checking the syntax of the statement in the language, programming language. So instead of this bracket, we are having curly brackets in C language. So number of left bracket and right bracket we want to try to check in the syntax analyzer. So matching parenthesis is a problem that is used over there. And here I've used the bracket inside. So nesting brackets are used. So for that, you need to write down the context-free grammar. So how to write it? We can divide this into two parts, left and right. So my S can be, or I'll say that S is equal to the left bracket, S is inside and the bracket. Or my S is equal to this first bracket opening and closing bracket and the second opening and closing brackets. So two types of recursions are possible. And then if you are having these two rules, then you get the freedom. Like for this S, you can apply SS. You may have two brackets inside. Or if you have only one bracket inside, then for this inside S, you apply the first rule only. So it will be two brackets and with the inside that S. And finally, to stop the recursion, you say S is equal to epsilon. Okay, so any doubt in this? Matching parenthesis, reply me on chat. For matching parenthesis, is there any problem? S, okay, correct. Lijo is also correct. Lijo is also correct. Have you understood this solution? S is equal to bracket S a bracket or S is equal to SS for 2 times, and any one of the S can be epsilon. Now the next problem: 1 star, 0 1 star, 0 1 star, then either 0 plus 1 star. So here for regular expression it is always easy. For 1 star you take a variable, and for 0 or 1 bracket star you take a variable. So S will be equal to X. This is the regular expression with at least two zeros. At least two zeros are needed. So sometimes only they will give you this statement. So write down the regular expression for that, and then you design the context free grammar. So at least two zeros means this at least two zeros are there, and before and after the zeros any number of ones can appear, and even once two zeros are over any number of zeros and ones are possible. So that's why I have this is a regular expression for at least two zeros. So here at least two zeros are there, and it can generate more than two zeros also. So the expression will be like S will be X 0 X 0 X and Y. And now you write down here the value for X. So X will be 1X or epsilon, and Y will be either 0 or 1 Y. So this will be either 0 any number of times or either 1 any number of times, and then epsilon. Okay. So understood now? Next problem. A raised to M, B raised to N, C raised to P, and D raised to Q, where M plus N is equal to P plus Q. It is given as M plus N is equal to P plus Q. So total number of A's and B's is equal to total number of C's and D's. Addition of these two, total number of is equal to this. Okay, so now how to solve this problem? So now there are multiple combinations. Okay, so this is a big problem. This is a big problem. Pay attention properly. What they are saying, M plus N is equal to P plus Q. That means number of A's plus number of B's is equal to, you get a number that is equal to M plus N. That is equal to number of C's plus number of D's. Okay. So what are the possible combinations? Your M can be greater than Q. Now we have to check and we have to convert it into A raised to N, B raised to N kind of equation. So I'll say that what are the first I'll compare A and D to write the rule. So for A and D, I can say that M may be greater than Q, or M may be less than Q, or M is equal to Q, and then I'll write down the rules. So for first time, if I'm assuming M is greater than Q, then number of A's are greater than number of D's. Okay, so I can rewrite this. I can rewrite this A raised to M. I can rewrite this A raised to M, and I'll say that for my word, I can write the word as A raised to Q, because M is greater than Q, so A can be there for Q times, and A will be there for M minus Q times. Are you understanding? I'm assuming for the first time M is greater than Q. If M is greater than Q, number of A's are greater than number of D's. So I'll split number of A's. Number of A's will be number of A's for Q times and number of A's for M minus Q times, and then B raised to N, C raised to P, and D raised to Q. If I do that then I'm getting A and D as equal. So if I'm getting A and D as equal, I can write the rule for that, and I'll have a variable for this particular term. So I'll say that S is equal to ASD, uh, or X. Okay, the Z is because of the next variation. Okay, so first, right now you ignore Z. Right now with this particular expression, I say that S is equal to ASD or S is equal to X. Now X is equal to this particular term. So X is equal to M minus Q, B raised to N, and C raised to P. Now again you try to check here like how we can go ahead with this to solve the problem. Can I represent A in the terms of P? So my M minus P will be equal to okay, or I can change C. C is equal to P. C is for P times. So check for P ka value. So P ka value can be M plus N minus Q. I can write down P in this equation. P is equal to M plus N minus Q. So I am just replacing this P with M plus N minus Q. And now here I am getting M minus Q. So I will again split that C, number of C's. And I can rewrite it as A raised to M minus Q, B raised to N, C raised to N, and C raised to M minus Q. So now it is simplified. So my X is number of A's here and number of C's here. M minus Q times of number of A's and C's. So I will say that my X is equal to AXC any number of time. To stop the recursion, I'll say that it is equal to Z. It is equal to Z. And if I'm saying Z, then Z will be B raised to N, C raised to N. So for that, I will have to write the rule as Z is equal to BZC or epsilon. Okay. And then here I'm writing it as Z because if my this Q is equal to 0. So Q is equal to 0, S will be directly equal to Z. Okay. So this is done for M is greater than Q. This is done for M is greater than Q. Now we'll see the next condition, M is less than Q. So if M is less than Q, then I will have the rule as um, I will have a rule as A raised to M. I'll rewrite D. If M is less than Q and D is for Q times, so D can be split into two parts. D for M times and D for Q minus M times. Similar to that. And now I'm having A and D as equal. So I'll write down S is equal to ASD or this particular term capital Y. So I'll take the capital Y now. Capital Y is equal to B raised to N, C raised to P, D raised to Q minus M. And then I'll try, can I write N in terms of this Q minus M? So N will be equal to P plus Q minus M. So I'll rewrite this B as P plus Q minus M and D raised to Q minus M. Again, you rewrite B as B for Q minus M time, B for P times, this Q minus M and P. And then Q minus. So again, it is simplified. B and D is similar. So I'll say that Y is equal to B by D, B, uh, B by D or Z. Okay, this is Y here. This is Y here. B by D or Z. And then Z will be equal to B raised to N, C raised to N. So Z will be BZC or epsilon. Okay, so this way it is going to work. Now the last condition, M is equal to Q. If M is equal to Q, then N is equal to P. And then to apply equation is simple. That M is equal to Q, so P, so this A and D are equal. So I'll say that S is equal to ASD or suppose Z. I'm taking the same variable Z because Z is equal to B raised to N, C raised to N, which is already there. So for this B raised to N, C raised to N, I'll say that it is equal to Z and Z is equal to B, Z, C and epsilon. Okay. And now you just combine all the rules together. Now you combine all the rules together, you see that there is a very repetition in some of the rules. S is equal to ASD and ASD for two times and three times. So we will take it for only for one time in the final answer. Then X or Z or Y, and then write down for X and Z. So combine all the rules and that will be the final answer. And you can say that G is equal to VTPS where S is equal to XYZ, S, and the terminal symbols are A, B. Okay. So any doubts in this? See, the equation is given to you, number of A's, B's and C's and D's are specified and some relation is given to you, and then you need to assume that M may be greater than Q, and then these are the rules. If M may be less than Q, then these are the rules. Or if M is equal to Q, then these are the rules. And either this is true or this is true or this is true. Any one of the condition is true. So it is a OR operation. So combine all the rules with the OR operation, and that will be the final answer. Okay, this way we solve. So now you can tell me the answers for the next. A raised to I, only 10 minutes are there. So please you write down the answers fatafat in the chat window. A raised to I, B raised to J, C raised to K, and I is equal to J plus K. How to split up? It will be A will be split into two parts. First, how to split? A raised to I, B raised to J, C raised to K. Split and write down. When we combine, do we have to write the condition? No, no. When you combine and when you write down the final answer, you don't have to say anything. When you solve it, that time you just say the answer. Say that for this condition, these are the rules. But when you combine, you don't have to say. A raised to K and A raised to J. Okay, so A for K times, and yes, right, because first we have to assume K. So A for K times will become equal to C for K times, and then A and B will become J times. So everything, all the problems are like that only. So S will be ASC and or X, and then X will be AXB or AB. Okay, so this is done. Now the next one is I've taken the same problem. No, it is not a same problem. Here they are saying J is equal to I plus K. J is equal to I plus K. Number of B's are equal to number of A's and C's. So this is also simple. Split the B into two parts. B for I times and B for K times. Okay. So we'll rewrite this word and it is equal to A for I times, B for I times, then B for K times and C for K times. So we are now getting this particular string. We can divide into two parts. This AB as a X variable and BC as a Y variable. So S will be equal to XY. And then I'll write down the rule for X, AXB or AB or BYC or BC. Okay, so again you have divided this. This B is divided into two parts, and then you are getting X for this part AB and Y for BC. Now next is A raised to I, B raised to J, and C raised to K, where I is equal to J and J is equal to K, or दिया है. So again it is or. So I'll say that if I is equal to J or J is equal to K. So I'm writing the rules here for I is equal to J and J is equal to K here. And then I'll combine all the rules together. That will be the final answer. So if I is equal to J, then this is equal. They are same. A and B are same. A raised to I, B raised to J. This particular left part is same. So I'll say that S is equal to A and B. Okay. Now for A, I am writing the rule as A capital. This is A raised to N, B raised to N. So A, B, or AB to stop the recursion. And for capital B, it is C raised to K. So it will be CB and or C. And here there is a condition that at least they are equal, greater than or equal to 1. Then for J is equal to K, this will be the term that I'm getting. I'm using two different variables X and Y now. So I'll say that X is equal to S is equal to XY. X will be equal to AX or A and Y will be equal to BYC or BC. Okay. So what I suggest you, because we are not solving these problems on the blackboard, I don't know how much you are efficient now by solving the problems. I will send you the list of all these problems, same problems, because I've taken all these problems from multiple books and internet and all. So I think I've covered all the problems which are there in the textbook and question papers. So I'll make a list of all these problems and without referring anything, you try to solve on your own. And if you're able to solve, then only you can say that you know this particular topic. Okay. So I'll upload that and you practice it. Now the next problem is 011 plus 1 string or 01 string. So it can be divided into two portions, X and Y. My X will be either 011X or 1X or epsilon. And Y will be 01Y or epsilon. Okay, so this was also simple. Then AB star is also simple. So S will be small a, capital B, and capital B will be B, small b, capital B, and epsilon. So B string के लिए. Okay, then A star, B star, A for any number of times, then B for any number of times. So S will be AB, and then A will be small a capital A epsilon, and capital B will be small b capital B epsilon. Okay, then again here again I and J के format में है I minus K is equal to J. The relation is I minus K is equal to J. That means uh, number of ones is equal to number of zeros minus number of twos. Okay, so I can assume some value of J, and I will rewrite the statement. So I'm saying that my suppose my K is equal to 2. Okay, so if K is equal to 2, 2 is there for 2 times. Then and my I is equal to 5. So I will be for 5 times. 0 will be there for 5 times. So 5 minus 2 will be equal to 3. So 1 will become there for 3 times. Okay. So it will be, I can split the word as 0 raised to I, 0 raised to J, 1 raised to J, and 2 raised to K. Okay, are you understanding this K? I minus K is equal to J. Suppose so I'm taking random values. If my K is equal to 2 and I is equal to 5, then my J will be 3. So if it is like that, then I will rewrite the statement 5 zeros, 3 ones, and 2 twos. So now how to divide them? So what I'll do is that I will uh, uh, separate 2 zeros out of 5. So 2 zeros and 2 twos. So they are equal. Now remaining are 3 zeros, and 3 zeros is equal to 3 ones. So what I can say that 0 for I times is equal to 2 for K times here left hand, and then 0 for J times will be equal to 1 for J times. That means okay, and then now you rewrite. So S will be equal to 0 as 2 and or X, and my X will be equal to 0 X1 or epsilon. This will be the answer. So I'll give this problem. We can solve this particular problem. This can be the last problem, and then remaining problems you solve it as a homework. A raised to n, b raised to m, c raised to k, where m is equal to n and m is less than or equal to k. Okay, the condition given is this, and or is there. So I'll say that suppose m is equal to n. If m is equal to n, then these two terms are same. So this is easy. xy and x will be a b के लिए and y will be for c for any number of times. Then my m is less than or equal to k. So if m is less than or equal to k, then m is less than or equal to k. So I can split b. No, no. M is less than k. That means I can split c. So I will write c for m times and c for k minus m times. Okay. So this is total will be c for k times. And now I can make the groups. So my first group is BC. And here I cannot make the group of A and C. So I will say that my S is equal to ABC. And A will be A for capital A for A raised to N. Then capital B for BC. And capital C for C. And now I can write down the final answer by combining. So like this, you need to write down the final answer. That S is equal to either XY or ABC or X के लिए rules, Y के लिए rules, ABC का rules, and then this is the final answer. Okay, so I have covered everything in today's lecture. So we have done sufficient problems of designing of context-free grammar. Same all these problems you try once at home. Okay, if you bought the books, then you refer the book of TechMax and solve all the designing problems of context-free grammar to practice it properly. Okay, so the practicing is must. So we can stop now for today's lecture. We'll start with the new topic tomorrow or the next lecture.